So let's start with this very simple cartoon picture of the life in a molecular cloud. So first you have molecules, and there's gravity, and then you have local collapse, and you start forming stars. And as soon as the stars turn on, they have stellar feedback, stellar winds and radiation. And this stellar feedback is going to destroy the molecular cloud and shut off further star formation. Later times you also have supernova explosions, and at some point the cloud will have dissolved and no more star formation can go on. So this is a very simple cartoon. Let's start with, let's go on with a slightly more complicated cartoon now. So let's start with a spherical cow in vacuum, our molecular cloud, top left. And let's look at different phases in the life of a molecular cloud. Let's start at the top left. So phase one, when the star cluster turns on, you have very hot winds which lead to adiabatic expansion of the gas around the star cluster. As soon as cooling becomes important, the very high temperature cools down, and the ISM around the cloud is now around the star cluster is now driven by momentum input from the star cluster in the forms of stellar winds and radiation pressure. So if feedback is strong enough, at some point the whole cloud might get swept up into a thin shell being pushed by feedback, and you might get small holes in there. And then the cloud can freely expand into the ambient ISM. There's also a different, so you can also, is there a laser pointer here? So there is also a dashed line, a dashed arrow showing you that you can directly go from the hot energy-driven wind phase to the free expansion if cooling is very inefficient. Okay, so now there are different fates for a molecular cloud. Either feedback is very strong, or feedback is not strong enough and gravity wins over. If gravity wins over, you can get a recollapse of the ISM and form more stars. If, on the other hand, feedback wins against gravity, the ISM will push to further and further distances, the pressure drops, the density of the shell becomes very low, and at some point the cloud dissolves. So how do we model this? It is easy to know how much wind momentum is being inputted into the cloud, but it's hard if you're talking about radiation. So what we use is a hydrostatic shell approximation. So we assume that the shell around the star cluster is in hydrostatic equilibrium, and then we can calculate how much radiation is actually being absorbed by the shell. So if you take a look at the black line here, which is density, and this is just a sketch. So R is the inner radius of the shell. The bubble on the inside of the shell is very low density because the winds in massive star clusters are very efficient to clean out the gas. So then you start, here's the shell, and the density increases. And in order for the radiation pressure and thermal pressure to be in balance, you need, on the inside the shell, the density needs to increase. So this is the ionized part of the shell, and then when all the ionizing photons have been absorbed, you have the neutral part of the shell, right? Which a much more higher density because it's much colder. And here's the outside, the ambient medium. With this approximation, we can calculate in a very simple 1D model how much radiation is being absorbed and how efficient radiation pressure is in driving the expansion of the shell around that star cluster. So I asked 3 questions in the beginning. And the first one was, what is the dominating source of feedback, if there is any? So if you take a look at the top left plot, so this is the efficiency of different kinds of feedback as a function of time. So you can see that for a 10 to the 5 solar mass cloud, initially radiation pressure plays an important role. Later, winds become more dominant, and at even later times, supernovae are the most efficient source of driving the gas away from the star cluster. This is different for a more massive cloud, a 10 to the 7, a very massive cloud, 10 to the 7 solar masses. So here you see that initially gravity is very important, trying to slow everything down, but the gas is still cruising along because of the initial very hot thermal pressure. And radiation pressure remains important even until late times in a very massive cloud. So we can now integrate the strength of feedback over the lifetime of the molecular cloud to see in what cases a cloud is dominated by radiation pressure and in what cases it is dominated by winds and supernovae. So on the x-axis you have the cloud mass, and on the y-axis you have the star formation efficiency of that cloud. And you see that in the top left corner, so for high star formation efficiencies and rather low cloud masses, winds and supernovae are dominating. Whereas if you take a look at the bottom right, for high cloud masses and low star formation efficiencies, you see that radiation pressure dominates feedback in a molecular cloud. So this is the first result. Let's go on with the second thing we checked, which is the minimum star formation efficiency. So again, a very simple cartoon picture here. You have a molecular cloud, it starts to form stars, feedback turns on, it's trying to push gas away, but if feedback is not strong enough, then the gas cannot be efficiently cleared away and you have more star formation, right? Until up to a point when you have formed enough stars to actually destroy the molecular cloud, you're going to continue with star formation. This is ignoring any triggered star formation in shells around the star cluster. So we can work out what the minimum star formation efficiency is needed to destroy a molecular cloud. So this is the star formation efficiency we expect a molecular cloud to achieve before it dissolves. So again, a similar plot as before. You have cloud mass on the x-axis, star formation efficiency on the y-axis, and the line, the dividing line between recollapse and continued expansion, even dissolution, is the dashed line you see over there. And this dashed line tells you what the minimum star formation efficiency is. So for example, if you take a 10 to the 6 solar mass cloud, it's going to need a star formation efficiency of 10% to get dissolved. So if it's higher, of course, it also dissolves. But if it's lower, it's going to continue with star formation until it hits 10% star formation efficiency. And if we work this out for different dependencies, so you can see that if you increase the cloud mass, the minimum star formation efficiency also increases. If you increase the density of the cloud, the minimum star formation efficiency increases. And if you increase metallicity, that's more complicated. You can take a look at the paper if you want, but the answer is not that straightforward. So the third thing I asked in the beginning was how much radiation escapes from a molecular cloud. And again, this is a very simple model. We're not taking into account any 3D effects of holes where you have a lot of radiation escaping and very dense clumps which will absorb a lot of radiation. This is just a pure 1D model where you can now work out how much of your ionizing radiation is escaping through the shell, if there is any. It could also be that all of the ionizing radiation is being absorbed. So this is for solar metallicity and for different density and cloud masses. But you can see that in the beginning, the escape fraction of ionizing radiation is low. And then after some time, 500,000 years approximately, ionizing radiation starts to leak out from the star-forming region. And then you have some variabilities, which are purely because of stellar evolution. So our star cluster is modeled via starburst 99 models. So we have the Wolf-Rayet phase, we have supernovae, the supernovae and Wolf-Rayet phases. They will increase the pressure on the inside of the shell. The shell will become denser, will absorb more radiation. So this is how you get variability. And we checked this. We also ran 3D models with Flash. And of course, now you have a lot of 3D effects. There's a hammer projection, similar to what you might know from the CMB. And red means nearly 100% of ionizing radiation is getting out. White means no radiation is getting out. You get a lot of variability. But if you if you integrate over the whole surface area, you get similar numbers as we get in our 1D model. And we also compared that to other papers. So, as I said, it agrees fairly well with 3D simulations. And we also found that you get higher escape fractions for metal-poor systems compared to metal-rich systems. So, I'm already close to the end. And I want to summarize what we did with our 1D code, which is called warp field. First, we answered the question, how effective is stellar feedback? Second, we checked what the minimum star formation efficiency is you need to destroy a molecular cloud. And third, how much radiation escapes from a star-forming region. We also took this semi-analytic model to another level and tested it against a real system, namely 30 Doradus, and answered the question, or began to answer the question, how it was possible to form a very massive cluster, R136, on the inside of another very massive cluster, namely NGC2017. And now we're working on doing synthetic observations and asking the question what an observer will see. And I think Eric, in the talk after this, will talk more about this. Thank you. Okay, so we take our numbers from Sturbus 99 models. So the Sturbus 99 model gets as the momentum from the wind, but it also tells us the radiation getting out of the star cluster, out of the star. And so I believe that is already accounted for.
More questions? John?
Really cool analysis, but I'm curious about, can you say a few more words about your assumption about the hydrostatic?
Yes, of course. So this model rests on the assumption that the shell around the star cluster is in hydrostatic equilibrium. This will not always be the case. In times where it's not the case, the model will be wrong. But if you take a look at real objects, many of them are actually in a state, many shells around very massive clusters are actually in a state of hydrostatic equilibrium, as Eric has, for example, showed in his papers. Orion, M17, 30 Dor. So we believe that the assumption of hydrostatic equilibrium, although not always valid, is probably going to be valid for a very long time during the lifetime of a molecular cloud. And we make a small percentage error in times where it's not true, but most of the times I believe we're right.
Any last questions? If not, thanks, speaker again.
A stick? Sure. I'll take a stick.
Usually there or on the other side.
Ah. Old school.
Well, it's very good. That's better.
I'm tall enough. It's fine.
All right. also on feedback, so we're continuing, is Eric Pellegrini, and take it away.
Okay, so I'm going to continue with Daniel's talk. I asked for the opportunity to switch talks from what the initial conversation was because Daniel was going to give a pretty good talk on overview. So I'm just going to go ahead and continue with studying physics and feedback based on some of the results from that model. I will quickly point out, so it's me and Daniel and Ralph and Simon at ETA with a few other people, but because our real ultimate goal is to not only test physics with observations, but then also to interpret the observations. We also have a large part of the work that I'm going to talk about is actually being done by Rodrigo Herrera Camus at MPE and then Mikael Rugel at MPIA. And the idea is to actually
26, 27, and try to see whether we can reproduce the velocity structures which we do see in W43 in our Milky Way. So then, going in the Milky Way, there are these large giant molecular filaments, which we have also talked here in other sessions already. Then, yes, we have 4, but it goes into smaller filaments, so that scale is on the order of 4 parsec lengths, and so we see interesting velocity structures in these kinds of filaments. What do these velocity structures tell us about fragmentation, yes or not? Then we come down to the scales of star formation and do this with the core program, which Heider showed yesterday, and not to forget there is ALMA, so we zoom in on much smaller scales on the order of 20, 30 milliarc second to dissect the star forming region at small scale. So my kind of goal is to really understand how these scales do connect and what we can understand from large to small, and where they also decouple and maybe not connect anymore. So these kind of things. Thank you.
Testing.
Ah,
Sorry, Henrik.
back to life.
Okay, here you go. Next up, Shen Yu.
Yeah.
Take it away.
Yeah. Good morning, everyone. My name is Shang Huoli. I'm a pre-dot in here. I'm working with Qizhou. So when I just come here in this February, I asked Qizhou, how many people working on the fragmentation using the dust continuum? And he said, almost everyone. So I said, well, excellent. I didn't even get my data. So, but finally we finished our observation and got the data in this August. And totally we observed seven high mass infrared dark cloud using the SMA in continuum and emission rise. And here showing fossils the dust continuum from the SMA observation. And with the SMA swarm creator and with 16 gigabyte hot span wise, so it can offer a mass sensitivity about 10 times lower than the global Jones mass. So we have a sensitivity to detect the high mass and low mass dense structure simultaneously. So, and then we can study the fragmentation in those very early evolutionary stage, which minimum effect by the stereofield bed. So, but ultimately we want to study the star formation of both high mass and low mass star in cluster environment. And actually, we also detect some very high velocity CO outflow in our sample. So it looks like quite a common as this high velocity CO outflow. Okay, I think I'll stop here. Thank you.
All right. Last but not least, Hector. We'll have a few more introductory talks before we head over to the conference as well.
Okay, thank you. Yes. I'm Hector Arce. I'm from Yale University, so thank you for letting me crash your party here. I'm gonna talk, well, lately, what I've been working most, it's with the Karma Orion project, Karma Orion data. This is one of the last, key science projects that Karma, was involved with. It's using, the Karma 15 antennas, to get the interferometer data and combining it with the Nobayama 45 meter data of Orion, most of the Orion A. We would have loved to continue down south, but well, Karma closed. So it's mostly using 12CO, 13CO, and C18O, 120. There are other lines, but those are the lines that we also have Nobayama data for. So the three main COs are topologs 120. So, just some highlights of the data. Well, we have a resolution of about 8 to 10 arc seconds. That's about 0.02 parsecs, I believe, at the distance of Orion. So here's a color movie where we're going up in velocities. and each, we're showing three channels at the same time. The middle one is green, and the blue one is blue, and the red is red. Some particular interesting features that can be seen, or that can be used for many things. Of course, outflows and shells. That's obvious. But there's all those things like small H2 regions, that could be used for studying what happens in H2 regions, but close by and less powerful than the ones that have been shown right now, just earlier. Mini pillars. Interesting striations, and filaments, of course. So this doesn't do justice to the data, but if you're interested in seeing more, please let me know, and I'll show you in my monitor. Thank you.
All right, so thank you to all of the introductory speakers. And next up we have a framing talk. So I'll just give you 30 minutes. Do you want me to give you a warning, like a 2-minute, 5-minute warning?
Sure. Oh, this is 7 o'clock for me too. Awesome.
Okay, I'll be right here, Peter. So.
All right, great.
All right, so Ian Stevens is going to be giving us a framing talk on the sub-parsec scales and telling us about a survey called Masses.
Okay, put this a little higher. Okay, so hi all. Where did that stick go? Okay, thank you. Hi all. Today, of course, I'm giving the framing talk on sub-parsec scales, and going to be talking about large-scale project with SMA called Masses. And so when framing sub-parsec scales, I mean, this is kind of a lot of scales. We're talking about, as Isla did disk yesterday, so about 100 AU scales all the way up to a parsec. That's about 3 orders of magnitude. And there's a lot of structures, and a lot of these different structures we could have whole conferences about. I'm just going to cover a few things and kind of briefly summarize some more recent work. So I'm going to talk about filaments and a little bit about cores and this kind of subfilament fiber idea, and a lot of protostars. And a lot of protostars is going to be kind of related to the Masses survey that we're going to relate. And since this is kind of short talk, your paper that you published about this, because I'm sure almost everybody in this room has published a paper about this, I'm not going to talk about it. So let's just get rid of that right away. And I'm also going to ask a lot of questions, and so this can be stuff that maybe can spur some ideas for some of the on-conference session. A lot of questions about all these topics, and once I ask these questions, we're going to think, hey, maybe we're not doing too good of a job at star formation because there's a lot of fundamental things we do not understand too well. So let's start with filaments. Okay, what do we know about filaments? So this is the chameleon cloud. It's very filamentary. It's fit with 2 different algorithms, the disperse algorithm in red, and then the fill finder algorithm by Koch-Modlowski in 2015 in blue that shows kind of the more diffuse filaments as well. So star formation is filamentary. A lot of times we talk about this universal line width, about 0.1 parsecs, and I think there's already a lot of contention in that already, because a lot of that depends on the method that you're measuring the line with, and maybe the size scale you're looking at, and whether it's high mass or low mass. But a lot of times you hear that number thrown out, about 0.1 parsec. And it seems like a lot of cores form where a lot of filaments come together at these kind of hubs that we talk about sometimes. So these are some kind of neat flash MHD simulations by Christoph Fedoroth, the 2015 papers. So what he does in these simulations is kind of add a few things at a time and sees what creates the filaments and how fast it creates stars within these filaments. So what we start off with the top left panel is just looking at gravity, and this is going to be gravity plus turbulence, gravity, turbulence, and magnetic fields, and gravity, turbulence, magnetic fields, and jets, feedback from jets. So if we kind of just go through the simulation real quick, we can see for the gravity-only simulation, the stars are forming very, very quickly, and we get this kind of filamentary structure. But actually, the filaments that are formed are too narrow compared to the observations we typically see, and star formation is extremely fast. If we add turbulence, we start getting filaments of the correct size, but again, star formation is more faster than we see based off observations. We add magnetic fields, the star formation rate decreases by a factor of about 2 to 3. Then when we add magnetic fields and jets, it reduces by another factor of 2. But both of these do create the kind of filamentary structure we see. And we kind of look at kind of brief graphs of the star formation efficiency versus the time per free fall. You can see this are adding individual components, gravity, and then plus turbulence, plus magnetic fields, plus jets. And we can see that it takes a lot longer to reach the star formation efficiency of 0.2. And so if we look at star formation rate versus time, and this is kind of where we expect the observations kind of constrain exactly where the star formation rate is. And we can see that the first three, gravity plus turbulence, and then with magnetic fields, we get above this the star formation rate that we typically see very quickly. And when we add jets, we start doing quite a bit better. So it seems like, hey, all these processes are pretty important in the star formation process. And just for people who know me, I like magnetic fields, and I just want to show some kind of images that we've seen with magnetic fields and star formation. Seems and more so star-forming filaments. We kind of can see a lot of these kind of recent filamentary structure. We see that magnetic fields are often perpendicular to at least these really dense filaments. But there are some exceptions out there as well. I'm kind of biasing, showing a lot of magnetic fields perpendicular to filaments, and I think there needs to be kind of especially with kind of blast pole and SOFIA coming out, more systematic surveys to see what exactly magnetic fields are doing in star-forming filaments. So as I promised you, here's some questions about filaments. So one question is, how do filaments form? Or a common, unconference topic is, what is a filament? And there's a lot of ways to form these filaments, and it seems like it could just naturally form from collapsing cloud. And there's also, models showing colliding flows work, and even colliding clouds can form a lot of filaments. And are these filaments constantly forming and dispersing, or do they form and they stay there for a mega year? We're not exactly sure. And what's even the shape of a filament? There's these ideas that they're cylinders, but there's also things, okay, well, if magnetic fields are significant, you expect them to be flattened a little bit. And so Saitenadi has had this idea of these magnetic ribbons that filaments actually are. And kind of like what's in between filaments, and how are filaments accreting from this, or is there mainly flow in filaments once they form? And I already talked a little bit about universal filament width, and a question I always like to ask, what roles do magnetic fields play? So let's get down to a slightly smaller scale, so the subfilaments. As you guys know, filaments, this is a filamentary kind of complex right here, and kind of towards these kind of hubs, we see a lot of things forming right here. And subfilaments can kind of be this kind of, or sometimes we call these fibers, are kind of within these filaments, these smaller structures that are kind of intertwined with each other. These are the two of them combined. The blue is kind of the filament, and the red's the subfilaments within these sources, and that's kind of the idea what subfilament or fiber is. And don't tell anybody, these are cosmological simulations. But, so this is kind of, I think a lot of people are very familiar with this image, the Hikari et al. 2013, showing this beautiful filament in torus and looking at velocity coherent structures, which call it either subfilaments or kind of fibers, and see that we have a lot of things intertwined. And here's a zoom in of B211 and 2213, and you can see all these, intertwining velocity coherent fibers. They find 35 of these structures in here, and the lengths are typically around half a parsec. The mass per unit length actually varies quite a bit. Typically it's around 10 solar masses, but up to about per parsec, but sometimes up to 70. And we see all these subfilaments are kind of in the same direction as the larger filament. And then Hikari Hikar et al. In 2017 published doing the similar analysis to NG1333, which is located kind of factor 2 further than torus. And they also found 14 velocity coherent fibers and with similar lengths as you saw previously. But in this situation, they found that the mass per unit length is actually quite a bit higher. And part of the reason maybe is because star formation is a lot more active. All these different fibers are fertile. In other words, they're all forming stars right now. And compared to the previous torus in this image, only about a third of these filaments were really considered as fertile and forming a lot of stars. And so maybe this is something naturally different with fibers in these regions. Another thing I just said, this is a factor 2 further away, and so they don't have the exact same resolution as try to maybe look at some of these fibers. So they might say this is the whole filament, and these call these fibers. Well, I might say, hey, well, this is a filamentary complex that we see, and maybe these individual things break it down into fibers. So I think we need a lot more observations to really understand exactly the role of what fibers are, whether they're universal or not. But we have done some simulations, and this is a great simulation by Rowan Smith in 2016 using SPH hydrodynamic turbulent simulations, so not including any magnetic fields. And these are just different times for times and star formations rates, and this is like the X, Y, Z, looking from X direction, Y direction, Z direction, or I guess that's Z and this is X. But as you can see, they trace these kind of fibers in the exact same way that you would expect from the Hikar et al. Paper, and they see that this kind of fiber, these subfilaments that you're seeing along these kind of major filaments right here, are kind of just natural. You naturally get these fibers, and they appear at the very beginning of the simulation, and they're ubiquitous. They still stay in the simulations throughout, and they found most of them are kind of more consistent with the first observations in torus, that most of them are kind of subcritical, and they're not forming stars, but there are a fraction that are forming stars. And these subfilaments in these simulations are actually kind of constantly forming and dispersing, except for the ones that form stars. So some questions on this is, can we trust fibers are actually real structures? I mean, we haven't really looked at the subfilament idea all that much. We are seeing it in many sources, not just these. And all filaments have this kind of hierarchical structure. Do fibers form after the filament forms? Do they form along with the filament, or do kind of filaments actually form from fibers? I think there's no consistent way of actually saying exactly the role of these fibers. And then, of course, what roles do magnetic field play? Are they going to cause more fibers? Are they going to make less fibers? I think it's quite uncertain still. All right, so on to protostellar objects, the smallest scale I'm going to talk about. And Masses talks a lot about this. I'm going to kind of talk about the stuff, just very briefly talk about some stuff that Masses can't do, and that's the really high resolution stuff. And this is recent results from the VLA Perseus Van Dam survey at 15 AU resolution. It's a very high resolution with the VLA by John Tobin. And what we're looking at here is just a histogram that's normalized to 1 of the log of the separation between binaries. So this is looking at really the fragmentation. And we're looking, from about 15 AU up to 10,000 AU, looking at binary companions and what does the distribution look like. And he found that it's a very significant bimodal distribution here as far as a kind of a peak in this area and a peak in this area. And this says that there's kind of 2 different ranges where we actually see fragmentation. And so we see it kind of at scales below 100 AUs, kind of disk scales, then at scales that are above 1,000 AU to 10,000 AU. And so this is actually kind of what we predict for 2 different fragmentation scenarios. One, the disk fragmentation scenario, where this protostellar disk and it fragments into multiple sources. And so at a small scale, it's disk fragmentation, then turbulent fragmentation at these kind of larger scales. And another interesting in this paper is John also noticed that if we just look at the class 1 sources, there's very, very few wide binaries. And given this sample size is kind of small, it is kind of enticing. And it says maybe these wide binaries that are creating actually eventually migrate towards each other to kind of form more tight binaries. But no, this is a small statistical sample, but it is kind of an interesting scenario. Or perhaps it's the opposite, that some of them kind of separate very quickly as well and never form binary either. And then the final thing, question kind of still related a little bit to disk is like, when does the disk form during the star formation process? Classically, we thought magnetic braking would cause disks not to get large until kind of the class 1 stage. But we're actually finding at the class 0 stage, the very young stages, we're finding very large disks, between 30 to 100 AU in size. And this is something that Skewer Cox found a good nine more class 0 sources that have profiles that are very disk-like. And Guerin et al. In 2017 is also finding some sources as well. So it does seem like a lot of disks can exist at the class 0 stage. So they form very, very early. So some questions. There's way too many questions about protostellar objects, and I think a lot of the high mass star formation communities kind of being like, hey, you're just kind of skipping high mass stars. But I do ask a few questions about this, and like our high mass star, do they have disks? Well, it looks like we're starting to find disks, but is it ubiquitous? Once they start ionizing a lot, do they sometimes destroy their disks, photoevaporate them? Another big question that I've always wondered about high mass star formation is like, can you actually find a starless high mass star forming core, or is there actually protostellar objects that are going to form instantaneously with the starless core? And so also is that just really discussing how does angular momentum transferred from large scales to small scales? Is it transferred? And I think we still don't even know where the outflows launch from the disk. We think it's from the disk, but you still have your X-wind models and disk wind models, and I think another very important thing is what do magnetic fields? What are they doing in all this process? All right, so that's the first half of the talk. I know I didn't cover everything. Again, it was impossible, but we got to talk about my stuff too. So masses, it stands for the mass assembly of stellar systems and their evolution with the SMA. It's a very long acronym, I think made up by Mike Dunham et al. And I have to try to memorize it every single time I give these talks, and I forget it a lot. But it's a continuum molecular line survey of every single class 0 and 1 protostar in the Perseus molecular cloud. And the very driving question is, how do stars really gain their mass? It's a large survey. It's about 600 hours or 600 good hours, or about 60 nights. And it took about 3 years to complete it. And the main kind of things we're talking about in the star formation process we really want to address with the surveys: conservation of angular momentum, outflows, and fragmentation. So, okay, what does masses, what is it observing? We use both the subcompact and extend configuration, which gives us scales between allows us to look at from 1 arcsecond resolution, 4 arcsecond resolution, with maximum angular scale about 5,000 AU. So we kind of probe between 200 and 5,000 AU. We simultaneously look at 230 gigahertz and 345 gigahertz, looking at continuum, CO2 to 1, other CO molecules, as well as N2D plus, HCO plus, H13CO plus, and CO. Again, this is for all known class 0 and 1 protostars. And the observations recently finished this January, and we already have several finished papers. Right here, we already have, looks like about 6 papers. And we have, a lot of results and a lot of different people working on it. We have undergrads, we have grad students, all leading papers, postdocs, and even faculty that have led papers with the masses data. And this is just some kind of quick image of what some of the outflows look like from the masses paper. A lot of these are pretty textbook-looking outflows, and some of these sources have never been observed with an interferometer before. And again, I kind of mentioned the Van Dam survey already. Big advantage we have of this situation is we know the fragmentation of every single one of these sources because we have ancillary data based off the VLA Van Dam survey. So we have 15 AU resolution, and we know the binary fraction of all these different sources, which really helps our analysis. All right, so the kind of subjects I will talk about with masses: accretion, fragmentation, outflows, and disk. And so let's start with accretion. This is a paper that Soren Freiman published earlier this year. What we're looking at right here is contours. The contours are C18O 2-to-1 contours, and the green is 1 millimeter continuum. And the idea of this paper is, can we use the C18O to see if accretion is gradual or is it episodic? So, and one way you can kind of test this is if you know the temperature, the bolometric luminosity of the source, you have an idea of where C18O and CO are going to freeze onto dust grains based off just kind of the luminosity of the star. And based off that star's luminosity, you can say how big you expect the CO region to be around each individual source. So what we can kind of do is just compare the current bolometric luminosity of the source and see the size expected on modeling and what we actually observe. And so the size expected on modeling is this blue line. So what we're showing here is the current luminosity of the star and the measured C18O size of the sources. And this is what we expect, is this blue line just based off our model, radiative transfer model. And what we actually observe are all these black points right here. And we see that it's significantly above this line, that our regions are larger than what we'd expect based off their current luminosity. And sometimes even a factor of 10 or 100 times larger than we would expect based off their luminosity. And so we say this is this can actually be expected by episodic accretion. So this is a kind of a cartoon that Jorgensen drew in 2015. If we sit there and think about the equilibrium state, we have CO frozen out here, and CO's in the gas stage right here because the star has particular luminosity and warming things up, releasing gas from the dust grains, so CO's in the gas stage here. All of a sudden we have this big accretion burst, the star lights up, and this equilibrium moves up to this direction. And once this accretion burst has calmed down and slowed and gone back to the original state, the equilibrium is back here. However, it actually takes time for dust to freeze back on the dust grains. It doesn't happen instantaneously, so you still can have this much larger region. And so kind of just based off a very simple model, kind of assuming a density profile and a freeze-out timescale, we can estimate how often accretion bursts are based off how big our regions are. And we calculate that accretion bursts are happening maybe every 20,000 to 50,000 years. And this is at the very young stages. People have looked at this for T-Tauri stars, and it hasn't been really, this kind of indirect method of trying to look at this, kind of this accretion burst, or sorry, this episodic accretion idea. And the JCMT has just started a survey also looking at episodic accretion by mapping big maps over and over again over time, seeing if there's some kind of episodic accretion events. And we're actually starting to see in these class 0 and class 1 stage that we do see episodic accretion, that stars, YSOs light up, protostars light up at these young stages. So going on to multiplicity and fragmentation. I'm not going to talk too much about this, but the idea is we have something we call it defined as a thermal genes mass. If something's above the thermal genes mass, we expect it to be able to fragment, and we define something called a genes number. The higher the mass, the more likely it's going to fragment. And we actually have kind of seen that in these kind of small areas in Catherine Lee's 2015 paper, that sources that have lower genes numbers and compared to sources with higher genes numbers fragment less. So this has a lower genes number. So this is SMA data. This is VLA high resolution data. We see that this only fragments into one source, and these fragment into multiple sources, and these have much higher genes numbers. And we have looked at this statistically for a lot of sources. This is Rouage's work. Talked to him more about this. We have seen this if we look at throughout the entire masses sample, that things with higher genes numbers are fragmenting a lot more. We actually see this at hierarchical scales. You saw this image briefly today or yesterday. All right, moving on to angular momentums and outflow. So the idea is if you have a cloud that's rotating you expect maybe the star is going to be rotating in the same direction. And another question is, well, what if in a situation of binary star formation, how does that fit in this kind of model? You have two different sources in here, and the cloud's collapsing. Do they both have similar spins if we have binaries? Well, this is one way we can look at it with masses. We look at outflows to figure out the spin direction. And we can see that we can measure the outflows. So we have two sources here, an outflow going this way, an outflow going this way, and we can compare the outflow directions and see if they're parallel, as we expect from one cloud collapsing and angular momentum being transferred to a small scale. And this is kind of what we actually see. So this is the projected angle between two outflows, and this is the cumulative distribution function. The step is what we expect, what we actually observed. So this is a histogram of what we observe. That looks kind of random. And this is what we expect for projected parallel angles. And this is perpendicular. So parallel looks like this. Perpendicular would look like this in just a general histogram. And then random as well, which is just a uniform distribution. We see that it matches more either this kind of random or perpendicular distribution. So it's not parallel. It's not one cloud that just collapses and all angular momentums transfer to both of them in the same direction, because we don't see that outflows are parallel, and they're significantly not. And this is actually a signature of binary formation via turbulent fragmentation. So Stella Offner did simulations as well, just including magnetic fields, and see that if we look at the, again, angle between two outflows and the cumulative distribution function observes black, simulations using turbulent fragmentation, of course, with magnetic fields, sees a similar distribution. So it's a signature of that. All right, so the last topic I'm really going to kind of talk about, and maybe talk about a few others if I have time, is does a protostar inherit angular momentum from its outflows from its natal filament? So if you have a filament, you might have multiple flows going on the filament, flows going through the filament. And a star that's forming in there the mass that's accreting on it could cause some kind of vorticity, and outflows could be made perhaps perpendicular to the filament or parallel to the filament. And so a thing you can do is just compare the filament position angle with the outflow position angle. And so if we get a Herschel column density map, we can kind of fit the filamentary direction of all the different sources. And then we compare it to the outflow direction, so the angular momentum of the star, and see, okay, is angular momentum transferred from these filamentary structures to protostars. And so this is kind of what we actually observe. So again, so in this situation, it's another cumulative distribution function, and this time we're looking at the projected angle between the outflow and the filaments. So the outflows we're measuring in masses, the filament direction we're measuring with Herschel. And what we actually see is this red step function here. And this is using the entire masses survey, and it shows really the power of this survey. This is where we expect parallel and perpendicular. And because we have a large sample, we can even say it's significantly not perpendicular with over 99% confidence. I mean, it's definitely not parallel, these outflow and filaments. But we can't distinguish it from random. So, and if you kind of just look real quick, this is the entire Perseus molecular cloud, and I kind of just drew the outflow direction for each one of these sources, and you can kind of see just throughout the masses cloud, it's really just kind of, everything's kind of randomly distributed. It doesn't matter where you are in the Perseus cloud. So it seems, regardless, if we look at things like the multiplicity or how the age or the column density, it seems like we're getting kind of these pretty random distributions between outflows and filament directions, regardless of what we see. But we can't just say it's definitely random, because we could do something simple like say, hey, it could be a mix of parallel and perpendicular, and we have a nice line that right here of 78% perpendicular and 22% parallel that fits this line quite well too. But what we can't say is outflows aren't always perpendicular and they aren't always parallel. There's something happening. It could be a signature of something like filamentary structure changing quickly with star formation, or we could also say that turbulent cores at these small scales is affecting the spin alignment to cause spin to be very random once we get into these smaller systems, these core systems, and they're kind of divergent of any angular momentum of vorticity that's happening at the filamentary scale. And I have time for maybe just one more quick topic that I wanted to discuss. It's a little bit more new and kind of talking a little bit about disk with masses. So masses has a beam that's typically in the subcompact configuration that's typically 1,000 AU, so this huge beam. Can we measure disk mass with a 1,000 AU beam? And this is some interesting work that we have done. So like I said, we have the Van Dam survey that has 15 AU resolution. We can look at these sources that look very disky, and from the Van Dam data we can get disk masses as well that we can measure better, because we can just model these disks and get the disk mass from these models, and it's an independent measure of what the actual disk mass is. And with our 1000 AU beam, we can compare that to JCMT data and do a correction based off the density profile that we assume and say, hey, this is approximately what we expect the disk mass to be. And so this is what's measured, the mass that's measured with Van Dam, and this is the mass that we measure with a 1000 AU beam. And we see this very strong linear, kind of linear relationship between the two, that, hey, what we're measuring at high resolution with the 1000 AU beam is very similar. And so it's actually, you can measure, at least statistically, disk masses with a 1000 AU beam from the SMA. And so this is something you can apply to anything. If you have ALMA and you're looking at something far away and you want to estimate disk masses, you can do it as well. So in summary, masses has done a lot of things. I'm not reading all this stuff, but there you go.
For questions and also discussion. So, does anyone open for questions?
I was surprised to see your the direction of the outflows was kind of random, just because of, if you're thinking parallel to filaments, kind of, you'd expect it to be going the direction of path of least resistance, right? So I just kind of wondered how much of an effect projection has on that result.
So yeah, that's a fantastic question, and I explained it very quickly. All these kind of Monte Carlo simulations, these blue curves, 100% takes in consideration projection. So like these parallel lines, what I do is I take outflows that are 0 to 20 degrees, and then I rotate them randomly in a sphere and see what that distribution looks like. So this totally takes into account projection. So, and the problem is, so you can definitely see it's definitely not parallel. But the path of least resistance, I guess, is the perpendicular. We can say it's significantly not always perpendicular. The problem is projection of perpendicular and random are actually not too far away. So if it's mostly perpendicular or random, we can't quite tell the difference between those two, unless you have even like a 300 source sample.
Yeah, so follow up to that. So I was noticing when you were sort of plotting some of the filaments, the filament directions that you were using to assign this, it seemed a little bit ambiguous in some cases. So how well do you believe that you assign a filament direction to a particular core, especially when you're at sort of like a nexus of filaments, for example?
Yeah, this is absolutely very good point and a hard thing to do. So I did two different things that actually, and I don't have time to show everything, but part of it is actually looking kind of the very large scale filamentary structure. So if we're looking at NG1333, that's assigned just all across the entire big filament. And then also looking at smaller scale, yes, you have things coming in at a hub, like what do you do with a hub? And some of it's just eyeballing what's the best kind of direction. But there's no definite great way to do that. But if you sit there and actually plot, all these outflow angles, even at these hubs or just along the filaments, if you kind of just look at this kind of more large-scale thing and kind of zoom in on each different thing, it still just seems random. But it's absolutely a good point. At these hubs, it's very complicated. What do you exactly expect at a hub?
So I remember at the Yale meeting, Stella Offner was showing the gyrating outflow. I forget how quickly those motions stop, but if you have an outflow being driven and then the orientations going wild, would we not just expect random orientations no matter what the overall structure was?
Absolutely. So that's one of the you know, I kind of showed Stella's simulations right here, and that's kind of what she kind of showed with turbulent fragmentation. That's kind of her interpretation. But I still wouldn't say this is definitely what's happening, because if we actually, some outflows that we see, even in the Perseus molecular cloud, we're seeing these huge outflows that are extending, you know, over many parsecs. Like these huge outflows that are very straight. Yeah. And I don't see a whole lot that seems to be processing, but I do see, like, not processing, but moving around. But I do see some. So they do seem, some do seem to move, some don't. So I think it's something we need to explore more.
And I think your point that you made towards the end about random could be, you know, 20% are parallel and, you know, whatever. There could be some, like, difference between the amount that's parallel and perpendicular. So there could be an environmental dependence.
Absolutely.
Listen.
This is really Hector's question, but he's not asking it. So.
Oh, what? You're going to ask why he skipped over the outflow stuff?
No. So Hector wrote this nice paper many years ago about the outflows themselves being episodic, looking at the mass-velocity relationship. And then we have this other stuff about PV stuff where also that's episodic. But the generations of the outflow, to which Shay said, can kind of overwrite each other. And so you can't see the history of what the position angle was. So if you do what you know, if you look for curving things, you won't see it. Because on the timescales you're talking about, where you talk about the mass accretion of tens of thousands of years, you have these huge bursts that come out in different directions, even in Stella's simulation. So it's even more complicated.
Absolutely, and yeah, I think someone has brought that up to me before. I don't know if it was Hector or you. It's possible both. And yeah, I think that is something we have to worry about. And you know, some of these outflows, yeah, we actually can see if we just assume kind of velocity. Yeah, well, we kind of have an idea about, you know, at least 10,000 years, but you know, these things form up to 10 to the 5 years we're looking at. It's yeah, we don't have the entire history.
So thanks for your talk. That was very interesting. So with respect to the orientation, relative orientation, we have a common problem. We have been looking into this. So there's statistical tools to do this. I don't know if you're familiar with the projected radius statistic and the VA statistic. We're looking into this. This is the way that people, for example, discover that cows are aligned with the magnetic field of the Earth. So this is a way of testing statistics that are basically periodic, so like angles. So there's some statistical tests that you can do other than just plotting the histogram that allows you to disentangle these populations and also allows you very easily to go from 3D to 2D and put some error bars in the statistical significance of what you're seeing. So you know that there's a bias towards parallel. There's many ways of projecting two vectors that are parallel, not so many ways in which they're perpendicular. And that is accounted for. So tomorrow I'm going to talk a little bit about that, but I can give you the references. So projected radius statistic and causal magnetic field. That's
okay. Yeah, email me those. I'd be interested. Thanks.
Well, I'm here. You can talk to me.
Yeah, that's it.
Great unconference.
But memory is not always best. But yeah, write it down there.
So you have this exquisite binary statistics. Did you try to calculate how much the specific angular momentum actually goes in orbital angular momentum of your binaries, or to get a complete picture of the angular momentum? Because you mostly talk about directions, but at some point I would also be interested what's the distribution of specific angular momentum over time as well.
Yeah, so we got a lot of data and not that many people to analyze it, and so C18O data, you know, the data should be public pretty soon. We got C18O data, N2D plus data, and you could conceivably do stuff like that, look at rotation profiles and things and measure stuff like that. The answer is no, we have not done that yet.
And there's complementary ALMA and VLA data.
That as well, so.
Ian, have there been statistical studies of luminosity fluctuations of protostars that would be detailed enough to test the idea that you mentioned in Sarah Freeman's paper?
The episodic accretion? Yeah, so at the class 0 and class 1 stage, it's pretty tough, and I kind of mentioned briefly there's the JCMT survey that keeps looking at certain protostars and keeps looking at the class 0 and 1 stage and keeps looking at them over a long baseline of time. And if you look at enough sources, and you can have an idea. And they've published a couple of results lately where they have seen some sort of luminosity burst of these protostars at the sub-millimeter wavelength, saying that there could be evidence of episodic accretion. And so that's an ongoing.
Frequent enough.
Yeah, and well, they detected 1 or 2 sources, and they've been doing it for a couple years. So apparently it does happen, but they haven't had a long enough baseline yet to say how common it is.
So can you give an update on the outflow opening angle stuff?
Oh, I have no update since the last thing you've seen. This is Mike.
Other people.
Yeah, we didn't all see it.
This is something Mike Dunham's working on a whole lot. Yeah.
I keep asking him too.
Yeah, and it's just basically looking at outflow opening angles and how they evolve with time. It seems like this is Hector's great result of kind of showing the time versus the opening angle to outflow, and we see the very kind of pretty convincing relationship that says, hey, at these really late stages, we're having these really wide opening angles and much smaller at a younger stage. And we kind of did it real quick. An undergrad did it, and looking at the age of masses, sources, and outflow opening angle, and seeing very random. And if we kind of look just at the very early stages of Hector's model, this is the class 0 and class 1 stage. We just look at his stuff, and I think we just looked at this. It's kind of random. I mean, we don't have a whole lot of really high points, but it's kind of random too. It's possible we're seeing something kind of similar, because you see the opening angle 100 right there. Most of our stuff's kind of below that, and we're kind of random. It's random at least below between 10 and 100 degrees. But no update on that. That's Mike Dunham's project he's working on, and he's teaching these days. So.
More questions? Okay, just one last question about the magnetic field. Someone has to ask about it. So if you have a strong magnetic field, that can help anchor the system. And I'm wondering if either the simulations, if those were done with magnetic fields, or what's known from the observational side about the strength of the magnetic field in those regions, in the filaments and then into the pores.
Yeah, I think, at least for the first molecular cloud, the actual strength is not too well constrained of what the magnetic fields are. Stellar simulations actually did include magnetic fields. Not like these very strong magnetic fields, but they do include magnetic fields, and they weren't, I can't remember off the top of my head what the alpha Mach number was, but it wasn't like super weak field, kind of weak. And what she actually saw, what helped, it actually helped them fragment into kind of more sources. So I can't find it right away. But the idea is, instead of having this global kind of collapse towards one source, if you add magnetic fields, it causes a flattened structure, and that flattened structure causes fragmentation of individual sources. And yeah, the field strength, I don't think she's tried a really strong field to see if they can keep that alignment, but as far as her simulation is concerned, it just makes a flattened structure that's more likely to fragment.
Any other questions, comments? Right, let's thank Ian again. And now we have 3 more introductory talks before we break for coffee. So, John, Anna, and Louis.
Okay, hi everyone. My name is John Forbes. I'm an ITC fellow here. I want to tell you briefly about one project I've been working on, and the goal of that project is to simultaneously fit all of these observed scaling relations that star-forming disk galaxies fall on. And the model I'm going to use to try to do that is this one. I take a disk galaxy and I divide it up into little logarithmic annuli, and I include all this physics, and then I evolve these galaxies from redshift 4 to redshift 0. Because we don't understand a lot of this physics very well, there's a lot of parameters that go into this model, and because it's a real radial simulation, it takes some time to actually run these calculations. So given this number of parameters and all that data I showed you, you'd want to do an MCMC, but it's basically impossible. So I've been working on a trick to make this much faster, which may be more generally applicable to some of you with models and a lot of data. And the idea is to use a much smaller subset of galaxies, to use it as a training set and run it through a random forest or some other machine learning algorithm, and then make predictions for all of these quantities that you want to compare to data. And then you can actually run your MCMC much faster. And here's an example of the results showing you that it's at least sort of working. So I probably have like 2 seconds per panel here. No. Yeah. Well, per panel, though. So the way this plot works is each column is a different redshift. The colored bands are data that I'm comparing to, and these points are resimulated galaxies after I've done the best fit and found the single most likely set of parameters. And then each row is a different relationship that I'm comparing to, and there's like 10 more of these rows that I'm not even showing you. And it works pretty well. So thanks.
Next up, we have Anna.
Hi. Okay, thanks. So I'm Anna. I'm a new Einstein Fellow here at the ITC, and I primarily work on numerical simulations to study feedback in massive star cluster formation. And so what I'm showing here is some work I did at the end of my PhD, that was a lot of my PhD, which was to better model radiative feedback in star formation simulations. And that's because in massive star formation, and for example, for dense massive star clusters and also for individual massive stars, you expect radiation pressure to be very important. Primarily the radiation pressure on dust, so the fact that the dust, these star-forming regions are pretty dusty, and so the opacity of the dust is very high, and so the direct radiation from the stars themselves will actually, the first absorption will actually be primarily absorbed by the dust with a high opacity, and then that dust will reprocess the radiation field and actually kind of enhance the radiation pressure in these star-forming regions. So to do that, spend a lot of time doing this hybrid radiation scheme in the Orion AMR code. It's adaptable to, I wrote a paper where it kind of explains how you can do this for any type of AMR code, where we do adaptive ray tracing for the radiation fields from stars, and also we use a different method to model the dust reprocessed radiation field. And I applied this to the individual massive star forming region to try to figure out, for turbulent cores, how do you overcome the radiation pressure barrier? And the fact is that you have these dense inflowing filaments that, even though it's not, spherically averaged throughout, you get that the dense filaments can overcome the radiation pressure barrier. I also like 30 Doradus, like a few people here. And so I also have done work to try to understand stellar feedback in massive star clusters. And I did some work focusing on 30 Doradus. And so one thing that we worked on was to trying to understand how does wind feedback actually couple to the ISM by using observations. Okay, so I'll just stop here and just say that what we found was basically that if you look at the hot gas, like if you look at the X-ray emission from star clusters, you find that all the wind energy is not contained within the hot gas, and that can give us an idea, at least maybe at later times after the star cluster has formed, that the wind energy that creates this hot gas that's due to the shock heating and winds may not be as effective as we might think. Thank you.
introductory talk is Hui Li.
Let's see. Oh, hi everyone. Let me change the gear a little bit for a larger scale. So I'm a postdoc at MIT. My name is Hui Li. So recently I'm designing a new algorithm to try to form star clusters in cosmological simulation. So in this algorithm, each individual star particles represent star clusters that are formed in the density peak of the molecular gas. And we use, so once the star cluster is formed, it starts to accrete mass from the adjacent to the environment. And I also include the stellar feedback processes so that this continuous growth of mass will be terminated self-consistently so that the final mass of the cluster is obtained self-consistently. We test this algorithm in cosmological simulations of Milky Way-sized galaxy, and we use the adaptive mesh refinement to overcome this huge dynamic range from this megaparsec simulation box all the way to 3 to 6 parsec resolution. So what we are trying to do at first is try to constrain the subgrid models in the cosmological simulations by the properties of star clusters. Because one of the main uncertainties in cosmological simulations is try to constrain these model parameters. And most of them are done by comparing the global properties of the galaxies with observation. For example, to compare with the star formation history of the galaxy and to match whether they are similar to observations. But what we found is that these global properties of the host galaxy, such as the star formation history, is very sensitive to the feedback intensity in the simulation parameters, but not sensitive to what you are doing on how do you do star formation. This means that you cannot constrain the star formation process or the feedback star formation parameters in this simulation by merely use the global property. It doesn't mean that you can do whatever you want in star formation. And what we find is that the properties of the model star clusters in our simulation is very sensitive to the choice of the star formation parameters. So in this way, we can have a brand new way to constrain the star formation in cosmological simulation. So if you're interested in this project, talk to me, or I have a poster. Thank you.
All right, and let's just thank all the speakers again of the morning session. We need to vote on the topic.
No, they need to add.
We need to add topics.
And then vote.
Alyssa will get on you. We won't be able to leave unless we
have
add a few more topics.
We have 4 up there, but we need some more from this morning so that we know what we're doing after this.
So I'm sure after all the talks, everyone's full of ideas for unconference. I think there's going to be a cow and magnetic field. So yeah, add topics and then we'll head over shortly.